Swayam Prabha. Digital India. Educated India.
Take a look at that. So let's just write what is our relationship 3. And again, this is not this is just a takeaway message which you will use in some of the problems. So let's take a look at that. So in relationship 3, what we have, suppose we are looking at an element, a small element as we were looking at before, right? And say this element at the left end, it has the the regular, our convention. So at the left end it has V M, right? And let's say on top of this element, instead of the distributed load, I have concentrated load. Suppose I have a concentrated. Now since it is a sudden load, the distributed loads are more gradual, whereas the concentrated loads are quite sudden. So you would appreciate or you would experience, the beam would experience a sudden change in the V and the M. So it is not going to be a delta X increase, maybe a slightly higher increase. So on the right hand side, I'm going to mark my shear force as V plus V1. Again, I'm marking in the positive convention, right? And say the moment, it changes as M plus M over here. And the length of the element over here, it still stays the same. The length of the element is still my delta X. Now again, if I write the force equilibrium, what I get is that if you write the equilibrium of just the vertical forces, what you will get is that your V minus V plus V1 minus P is equal to 0, which tells you that your V1 becomes equals to minus P. That is, your shear changes by an appreciable quantity with the load, right? And if you remember, when we were drawing our shear force diagrams and bending moment diagrams, that is what we had seen, that the say the shear force diagram was continuing in a constant manner. Then you had a point load and you had a sudden dip, right? So this is the reason for the dip. So you have a shear force over here, and as the sooner you're experiencing this force P over here, you're going on, and your sign is change, your magnitude of the shear changes all of a sudden. It sort of bumps up. So this is one relationship that is there, that your shear undergoes an appreciable change. Now let's take a look at the moment that is there. So if you take a look at the moment, the equilibrium of the moment, and if I say, let's say, take the moment about this particular point over here, what you will get is that your M plus M1 minus M plus P times delta X over 2, because if this is delta X and let's say the P acts at the center of that one, minus of V delta X becomes equals to 0. So essentially from here, what you can write, that your M1 is nothing but V delta X minus P delta X by 2. Now if delta X is very small, the change in moment is actually very less over here. So the moment does not go an appreciable change. So two important things we learned from this relationship. Number one is that your shear changes by an appreciable magnitude. So maybe let's make a quick note of that. So first point is that shear, and relationship 3, let's write it over here for a concentrated load. So the shear changes by an appreciable amount, and the moment, the change in moment over here is negligible because it's dependent upon that small length that you have over there. So the moment change is negligible. Okay, now that we have the relationship 3, let's talk about the last relationship that we would have, where you can understand. So this was for a concentrated load, so next we are going to have a concentrated moment. So let's write that down as well. So relationship number 4, so this is for concentrated moment. So again, let's take the same element. So if I take, another small element over here, where you have the force V and M, and here let's say we have a couple, a point couple. So the point couple meaning we have, something like this over here, which is acting. We have, say, a point couple, a concentrated moment acting at that particular point, and let's say the magnitude of that one is m naught here. And since I'm going to the right, and say, let's say I'm expecting some appreciable change in shear and appreciable change in moment, how am I going to mark in this one? I'm going to have a V plus V1 and an M plus M1 particular point. Now, if you balance the forces, if you balance the forces in the vertical direction, or essentially the shears, you can quickly tell that your V1 goes to 0 over here, because there is no point load over here, and this V and this V cancel. So your V1 is essentially 0. So this tells you that your V1 is essentially 0. That means that the shear has no change, absolutely no change at all. Now let's take a look at the moment. What happens to the moment? If you write the moment balancing equation, what you would get is that your M plus M1, which is, this guy over here, minus M minus V times delta X, where again this particular length that you see over here, that is my delta X over here, right? Plus m naught is going to be equals to 0. So what that tells you is that your m1 is equals to minus m naught. So this tells you that the change in moment is actually quite appreciable, similar to the previous one where we had the change in shear was quite appreciable. So here also, like we made these 2 bullet points, we can take 2 more, we can make 2 more bullet points for, this particular case over here. So let's go ahead and make them. So one key takeaway is that for the case where you have the concentrated moment, so in this particular case we are going to have the negligible or pretty much no change in shear, and the moment changes by an appreciable quantity. Appreciable change in moment. So overall, we looked at 4 relationships, and these 4 relationships, this explanation was necessary for you to understand that how these relationships come about. Now I'm going to summarize all these 4 relationships in maybe one single sheet so that you can keep it in your mind, and when you solve the problems you will see that how in the different places you use these different relationships. And as I said, compared to the traditional technique of your method of sections or the classical approach, you will see how much this makes your life easier while you draw the shear force diagrams and the bending moment. So this video is meant to be just a summary of all the relationships you looked at in the previous video, where we derived in details how the relationships between the load, the shear force, the bending moments come about. Right? So this video will just focus on the key features, the key relationships we looked at with a little bit of a brief explanation. So let's go ahead and take a look at it. So as we discussed that when you have bending moment problems or shear force diagram problems, that you are given a beam with a certain type of loading and you're supposed to draw the bending moment diagram and shear force diagram, you can do it using the classic approach or the method of sections, which we used in all the previous examples that you saw. Or the second approach to use is the relationships between the loads, the shear force, and the bending moments, and that is what we had looked at in details. And here we are just going to summarize the key points. So what we have over here is that, so we are going to look at the relationships between the shear force, between the load, shear force, and the bending moment. So let me scroll a little bit below. So what we have essentially here is that suppose you have a beam with a certain amount of loading. So we'll come to the text part later. So we have a beam with a certain amount of loading, right? And in the beam you have a point C and a point D. So this is maybe part of a bigger beam. So if you want, maybe this is part of a bigger beam. So you have maybe a beam with a certain, say, loading conditions and so on. And intermediately you have taken 2 points C and D. So this is what you're seeing over here. So this is a part of this, this chunk over here, C and D over here. This is what you're seeing, right? This is the chunk. So if you take a look at this particular chunk, what the first relationship we looked at, so let's maybe write that out. So this is our relationship number 1. And you may call this as 1A. So what we saw was that your dv dx, so you see here is the loading diagram, and corresponding to the loading diagram, in between the same 2 points C and D, you have the shear force diagram and you have the bending moment diagram. So let's just mark those as well. So this is our SFD and this is our BMD. So what this relationship says, the first relationship 1A says that the slope of your shear force diagram, that is dv dx. dv dx is nothing but the slope, because remember that the shear force diagram is a plot of the shear force with respect to x over here, which is along the length of your beam, right? So the slope of the shear force diagram is negative of the load, which is acting on the negative of the distributed load. Now very important, I noted this in the detailed detailed derivation of these equations, which we're doing it in the previous video, is that you have to bear in mind that this is derived by assuming the load is acting vertically down. If the load was acting vertically up, right, then this would be a positive. Okay, so dv dx equals to minus of wx, which means the slope of the shear force diagram, that is this slope, is negative of the distributed load which is acting on top of that, right? So this is our relationship number 1. So this is an important relationship. Now as you can tell, that is will be equal, this if w of x equals to 0, you don't have any distributed load, then your shear force will be a constant line. dv dx will be 0, so that means the shear force v is a constant. When your derivative of something is 0, that means that particular quantity is a constant quantity. And it is also true between concentrated loads. So if you have two concentrated loads and in between no distributed load, so that means your shear force diagram will also be constant. Now the second relationship, the part A for second relationship of the first one, that is A and B. So 1B says if we just integrate this particular equation over here, what we get is that Vd minus Vc is the negative of the area load of the negative of the area of the loading diagram between C and D, which is nothing but, if you go from this relationship to this one over here, this is essentially integral from xc to xd. We have derived this in the detailed video that you have, minus wx dx. What it says is this one over here, that the difference of the shear between the point D and the point C, remember C and D are 2 points, the original beam, the difference of the shear force in between them is the negative of the area of the loading diagram between C and D. So from C to D, if you take this whole entire area, VD minus VC is negative of this particular area that you have over here. So I hope the first two relationships are correct. So let's maybe mark this relationship as well. So this is the part B of the relationship we looked at. Now coming to the last relationship, or the relationship 2, which again relates your W to the moment. So let's just write that down. So this is our relationship 2. So the relationship 2 states, so if this is my 2A B. So 2A, similar to what we had over here, 2A is the derivative of the moment. So this was a derivative of the shear, this is a derivative of the moment. So the moment diagram. So the derivative of the moment is equal to the value of the shear. So that means the slope of the BMD. So if this is your bending moment diagram, the slope at any particular point is equals to the shear force at that corresponding point. That means that the slope at this particular point over here, this is where your MC is, this is the line of your bending moment diagram. The slope at this particular point is equal to the value of the shear at that particular point. Slope at here is equals to the corresponding value over here. Okay, and as we did in the previous one, if you just integrate this one, what you get, MD minus MC, that is the difference of the bending moment between the point D and the point C, that is MC minus MD minus MC, that is this difference over here, is negative of the area of the shear force diagram between C and D. Sorry, this will be a positive, it is not a negative, because as you can tell, if you just integrate this one, so that's about the typo over here. I will upload the corrected note. So this is not negative. So it is the area of the shear force diagram between C and D. This is very obvious. So if you just integrate this one between XC to XD, this also gets integrated. The integral of V dx is nothing but the area of the shear force diagram. So again, the MD minus MC is the area of V between D to C. So if you just calculate this entire area, that will give you the difference of the moment between D and C over here. Okay. Now, in addition to these two main relationships, we also looked at two other relationships. So let's quickly go to that one. So this one was our relationship 3, which stated that if you have an element, remember the previous relationships we looked at all relied on having a distributed load between the points. Now in this one, instead of having a distributed load, I have a point load. So when you have a concentrated load, what we saw that your M1 tends to 0. So essentially on both sides of the beam, you have literally no change of the moment, but V1 is quite sufficient. So V1 was in this particular case for this direction of the loading. If you look into the detailed video, what you will see, this gives you that your V1 equals to minus. So you have an appreciable change. So that means there is a jump in the shear force diagram, right? So essentially, if we just have to read it out, says that the presence of the concentrated load causes a jump in the shear force diagram and does not cause much change in M. Similarly, this was a concentrated load, and if you have a concentrated moment over here, so that leads us to our last relationship, that is relationship number 4, which says that if you have a concentrated moment, so that gives your V1 as equals to 0. So this V1 tends to 0 over here. So let's V1 becomes 0, whereas M1 is quite appreciable, and in this case for the given direction of the moment, M1 comes out to be minus M0. So there is a jump in the moment, but there is no change in the shear. So this is what it says: presence of a concentrated moment causes jumps in the bending moment diagram and does not cause much in V. So I hope this summary sheet is clear to you. If you want to get into more into the details of this one, of the different relationships which we derived. So please take a look at the detailed video in which you will get these relationships. The first relationship 1a 1b, and you will also get this 2a over here and 2b. Then each of the 1b and 2b are essentially integrals of the previous relation have, and also these relations. Now that you have the detailed content and you have the summarized content as well, please go through that. So later we will solve several different problems and you will see how easy your life becomes when you are using these particular relationships between the loads, the shear forces, and the